Chapter 2, Section 7. Well, we're going to talk about solving inequalities again. The biggest part of this is translation from English to algebra again. There are a lot of words and phrases that we use to translate to inequalities. And I think probably the biggest reasons there's so much language involved from the English language is that in the real world, inequalities are more common than equalities. There's very few things where we're going to run into real world situations where you have exact values for something that could make an equation. We're usually talking about some of the things we're going to talk about in these phrases are a lot more common in real world stuff. So inequalities are more useful most of the time in solving applications. So with that said, let's talk about some of these translations, and I'm going to bring up some problem solving techniques. In fact, the first thing they say in this section is that you should use the 5 steps of problem solving that can be used for problems involving inequalities. And you can go back 2 sections and they give you those 5. It'd be good to review that. And one of those happens to be in the familiarize section of that. They had like 8 steps just to familiarize yourself with word problems. And in the one I use, I worded a little bit differently. I talked about it before. Is doing a simpler problem. In other words, I'm going to throw some numbers at this thing that they're talking about and see if it makes it true or not. And usually that makes it easier to figure out which way I'm going to do my equal sign. It's kind of like when I talked about one of the big translations issue has to do with subtraction, because subtraction has to be done in the right order because it doesn't have the commutative property. So when I say 5 less than x, a lot of people will make a mistake and write that as 5 minus x. But if I threw some numbers at it, and if I say 5 less than 7, you wouldn't write that as 5 minus 7, you'd write it as 7 minus 5. Well, that's called doing a simpler problem. Throw some numbers at that. See, basically I threw numbers in there that I know the answer to this thing. So then I end up possibly rewriting the subtraction to make it fit what I know the answer should be. That's doing a simpler problem. And we're going to use this through some of this translation stuff. Let's start going through this. Important words, like used to be of meant multiply and those kind of things. Well, they're going to really focus in on, and to be a comparison with equations, it would be like is and was, are translations of the equal sign. Well, all these are going to be translations of inequality symbols. And so we need to know how to translate this. So this first one is at least. Now it would be looking at that again just in itself. It would be easy to make the mistake that means less than, or maybe less than or equal to if you guess. Well, then let's look at this. Like if I just, even before I go to these other sentences, if I said something like, if I think it's less than, I would say 5 is less than 10. Hey, that's true, right? Well, let's use the words. 5 is at least 10. Well, that doesn't make sense, does it? Well, that's doing a simpler problem. So it must be something else than this less than symbol. And I'll come back to that a few times. But let's go through the translation. A sample sentence might be, Kelby walks at least 1.5 miles a day. There it'd be easy to throw some stuff. Well, some days would Kelby walk 1 mile? Not according to this. It says Kelby walks at least 1.5 miles a day. Well, could Kelby walk 2 miles? Would that fit this condition of this sentence? And you'd say yes. So the values that we don't know, or the variable portion, is going to be greater than 1.5 is what I just tested. Now, what if she walked 1.5 miles? Would that make it true? Kelby walks at least 1.5 miles. Well, this day she walked 1.5 miles. Did she fit this sample sentence? Yes. So the other part of that inequality is that it can be equal to 1.5. So we would translate this if we said k is the amount of distance she walks in miles. I define my variable, right? Then I would know that whatever that variation of miles that she walks each day in miles, which I'm calling k, is greater than or equal to 1.5. Well, here's at most. Is at most. It says at most 5 students dropped the course. Now, what if 6 dropped? Would that fit this? And you'd say, no. If I said 4 dropped, that would still fit. So we're looking at numbers that are basically less than 5, but are also equal to 5. So throwing numbers at this thing does this. Also, I need to think about the definition of a variable. I see a lot of times, we're getting into more and more, not necessarily complicated stuff, but it's a little more complex. There's a little more stuff to think about with each thing that we're doing, and we tend to forget the simple definitions back from chapter 1. Like, what is a variable? Well, I need to define that. Say, this n that I don't know in this case, where they say let n represent the number of students who drop the course. I might start there and say, well, if n is this thing, well, what if n was 2? Does that fit this? Is 2 at most 5? And you'd say yes. So what is 2 to 5? It is less than. And that gives me a direction for my inequality symbol. Or another way to read this is n, this set of solutions, which is an infinity, possibly. Not, well, when we're talking about whole people here, this is not an infinity. We would have either 0. I don't think I'm going to have negative students unless they've taken a lot of tests and are mad at their teacher, and that's a bad joke. But anyhow, the actual solutions to this thing in a real world thing would be 0, 1, 2, 3, or 4. Or one more, too, which is 5, because it can be equal to 5. Where a lot of times like this one, truly Kelby could walk 10 miles, or 11 miles, or 12 miles a day, those kinds of things. There's really an infinity of solutions. Probably realistically there's an infinity of fractional solutions that would occur, because there's probably a maximum that you can walk in a day for any person. So, and in this case, there would be a finite, because we're talking about not fractional students, right? So anyhow, we get that by going through, define the variable, and then put it into an algebraic expression with an inequality. Well, here's cannot exceed. Now, if I think about that, I cannot exceed, in this case, $12,000. If I'm out looking for a car and I can spend $12,000, that means I cannot exceed the $12,000 mark. So what would be the inequality? Or if I thought about this, does that mean that I can only buy cars that are $12,000? And you say, no, I could find a car for $10,000. That would still fit into this condition or this inequality. So the cost of whatever I'm looking for needs to stay under or less than, or it could be exactly right on 12,000 when it's here. So we could write this as C is less than or equal to 12,000. Or this set of solutions is left of, that points to the left, that's from the arrow on a number line. C is left of or right on 12,000. Must exceed, the speed must exceed 40 miles an hour. And I haven't seen signs like this. We used to see sometimes you'd see signs on 4-lane highways, and I think it was more to keep farm traffic off those roads, where they would say you have to go over a certain miles per hour and those kinds of things. So the speed must exceed 40 miles an hour. Well, that means that the speed, can it be 40 miles per hour? So I start throwing numbers at it again. Well, it does 40 exceed 40? No. So it's not equal. And then would 50 exceed 40? Yes. 60, 70, and so on. Would 30 no. Exceed 40? No. So we're basically, by substituting in here, I can figure out what my inequality symbol needs to be. In other words, this speed needs to be right of 40 on a number line. This points to the right, and so on. Is less than translates pretty nicely. Is more than translates pretty nicely. Though it could easily get confused with at least, and is at most. Now, this one is a little bit, I think in the real world we're used to seeing these kinds of things. The key here is, how do I translate this into an algebraic equation or inequality? And it says it is between. The film is between 90 minutes and 100 minutes long. So the time, if I say t is time, represents the length of the movie, then I can start throwing some stuff in here and say, well, could it be 80 minutes? No. It has to be bigger than 90 and smaller than 100. So I end up with a situation where 90 is less than the time, and the time is less than 100. So we can write this compound inequality. Minimum indicates that the minimum you can have for anything means that you'd have to at least make that marker go over the mark. In other words, the W they use for the variable, which represents the number of glasses of water that Ned drank, W has to be greater than or to the right of 5 on a number line, or equal to 5 or right on the same spot as 5 on a number line. So there's greater than. Maximum means it has to be less than, but it could also be equal to it. No more than is similar to maximum, and no less than is similar to minimum. So a lot of language there. It would be good to have this page available while you're working on these word problems. The following phrase, and then they have a little square around it. These phrases, at least and at most, deserve special attention. And it says the quantity x is at least some amount q. Well, we would write that as q is greater than or equal to, did I say q? I mean x is greater than or equal to q. If x is at least q, it cannot be less than q. Okay? And the reason they're going through this language again, right here again with at most, is that there are a lot of errors around this stuff. I would go back to putting numbers in there. Put numbers that you understand in there. Do a simpler problem with what they're trying to tell me. If I say 2 is at least some amount, which is some amount q is 2 is at least 3? And you'd say no, it didn't make it to 3. Is 2 is it at least 1 if I keep that 2? And I start seeing which way my inequality has to occur. So 2 compared to 1 is greater than or equal to 1 is what fits this statement, and then vice versa with at most. So let's look at some of the sample problems here. It says catering costs. To cater a party, Papa Rowe charges $50 setup fee plus $15 per person. The cost of the hotel, pharmacy, and a season softball party cannot exceed $450. How many people can attend the party? Now, if I just stop there and say cannot exceed, what is the inequality symbol? Because the goal to this, and the other thing I see students do a lot of times, all of a sudden you start getting into word problems and you forget that you're in algebra class. The key is that we're trying to translate these things into equations and inequalities and then solve those things. Now we do a lot of things to familiarize a lot of the stuff that they're doing, like here at the beginning of this, they're going to go through the steps to work out applications, is we start thinking, hey, this is the process to just guess and check at the number and find the number. And a lot of the problems that we do in the book, especially examples, you probably can get away with that. Boy, but as soon as I start throwing some fractional answers in there, you're going to spend a lot of time guessing and checking. So remember, the goal is to come out with an algebraic inequality in this case. So here's what they do. Well, if I say, well, got a certain amount of money that I can spend right here, it cannot exceed $450. Well, would that mean that I could spend $430? And it obviously, you see, yeah, that's true. Could I spend $460 or $500? No, I can't go over that mark of $450. So I need to start queuing up the idea, what inequality symbol am I running into? And if you start there right here, we're going to know that we're going to have less than or equal to 450. Now, whatever happens in the front of this is the same translation process we did when we were working with equations. But this cannot exceed comes back into this right here, this part here, how I translate that. Okay, they go through this, familiarize this for this problem. It says, suppose that 20 people were to attend. In other words, I start throwing some numbers at this again. I'm basically setting up a simpler problem where I have the inputs and I see what the output for cost would be. So they say, well, let's pretend 20 people are coming. What would happen? Well, I have this setup fee of $50. I get that no matter how many people I have. So I'm going to have $50 plus $15 per person. In this case would be 20. So I take 15 times 20 and then add $50 to it, and I end up with $350. Now this shows that more than 20 people could attend without exceeding $450. It also, I would say, tells me, hey, it's less than $450. 20 people could attend this and I'm still okay according to my conditions. But really what they're trying to do is, how do I translate this into an inequality? And then it says, instead of making another guess, let's say n is the number of people in attendance. And if I look at what I got here, I'd have 50 plus 15 times. Now we replace that 20 with n, and now I have an expression that I can use. And that's what they're showing here. So to translate, I end up with a setup fee of 50, which is added on, plus the cost of the meal is $15 per person. Now I don't know what the amount of people coming are, so that's my variable. Cannot exceed is less than or equal to this dollar amount of $450. Now I have an inequality. I can solve this. I can add 50 to both sides, negative 50, excuse me. They say subtract, same as adding negative 50. I end up with an equivalent inequality. In other words, this inequality has exactly the same solution set as the original, because I followed the rules of using the addition principle. And then I use the multiplication principle of taking both sides by 1 over 15, or they say divide both sides by 15, which is the same as multiplying by the reciprocal of 15, which is 1/15. Now I wouldn't go through divide then reciprocal. I'd say, well, the reciprocal of 15 times 15 is 1. I want 1n, so I take 1 over 15 times 15. I get 1 times n, which is n. And then I take 1/15 times 400, and I end up with this 26 2/3. Or if you simplify the fraction, I think 5 goes into both of these, goes in here 3 times. 5 goes in here 80 times. And I could say 80 thirds. But probably, what are we talking about here? People, right? So if I wanted this to come out, if this was an equation, like I said, inequalities happen more often than equalities. If this was an equal sign, I would have an answer that makes no sense at all. It would say that I have to have 26 and 2/3 of a person come to my concert or my party, which doesn't make sense. So with an inequality, it does though. My number of people coming to the party has to be less than or equal to 26 and 2/3. Could 26 people come to this and still keep my cost under $450? Yes. But 27 can't. If I go to the 27th person, I've exceeded this $450. And then the other key part to this, even though I've written this inequality and everything else and I've solved the inequality, if I answered this question and said 26 and 2/3 people, that would be a pretty ridiculous answer to how many people can attend. And what they want us to do is state it in a sentence. And I would say, how do I communicate that? Well, I could say at most 26 people can attend this party. Or I could say 26 or less people could attend this party. There's some different ways I could state this answer. But it would make sense to the question. If I go back to the original, that's what they want to know, is what is the most amount of people I can have come to this party with these conditions that we've set up. And then they have another caution here. It says solutions of problems should always be checked using the original wording of the problem. So you go back to the original deal and say, I came out with this inequality meaning this. What does this mean as far as knowing what the solution should be to the question in this word problem? And that's what they're talking about. So go back, make sure you have a good answer to the original deal, and also that it makes sense. I take this information back into it, and could I put 26 in there and find out how much it would cost? Yes, you could. Well, the next deal, they have a box here. They talk about average or mean, or another way to say this is, well, we'll just stay with those words. I'm not going to throw some more at it because we've got a lot of words. And what we do to do this average, is to add up all the numbers in this set, and then you divide by the number of things that you added. That gives us an average. It's really a statistical tool to say, what's going on. We do this a lot with classes. Sometimes I'll send out a message after everybody's taken their test, and I'll say, well, the average score for this test, just to give you an idea where you sit in the class. It isn't a perfect tool, but it gives you a little bit idea where you're at. And you say if you got an 82% on your test, and you're going like, wow, I got a low B, and I'm kind of worried. And then I came out and I said, well, the average score for this test was a 65%. Then I would feel better about that 82%. Now, if I came out and said the average score was 90, and you got an 82, then I'd get a little concerned, right? So it's a good way to communicate generally what's happening with a set of data or a group of scores is what I'm talking about, those kinds of things. So we use mean or the average in a lot of different things. So example 2 is talking about financial aid. It says full-time students in a healthcare education program can receive financial aid and employment benefits from Covenant health system by working at Covenant while attending school and also agreeing to work there after graduation. Students who work an average of at least 16 hours per week receive extra pay and part-time employee benefits. For the first 3 weeks of September, Dina worked 20 hours, 12 hours, and 14 hours. How many hours must she work during the fourth week in order to average at least 16 hours per week for the month? Which is an important number, right? And it's not an equal to. It's how many, it's really an inequality. Is that you can go over that. In fact, if you go over that, you're going to make more money, right? So if they're going to allow you to go over that, great. So we familiarize this so it really is an inequality, but they start doing some stuff with like, how do I deal with averages? What does that mean? Those kinds of things. And if I knew how much actual hours she worked on that fourth week, I could throw that in and I could probably figure out what the average would be, right? So let's look at that. And that's what they're doing. They say, well, let's put these hours of work for these 3 weeks, and let's just guess that the fourth week she worked 10 hours. Well, if I added those up and divided by 4, I get 14. Well, if she did work 10 hours that week, she didn't make her minimum, right? And would not lose some benefits. So what we do, again, that familiarize step, is to help us to write this expression with the variable. The variable is what we're trying to find the solution, or what values will work in here. So I do that same addition, but instead of throwing a number at this unknown, right, is I put in a variable, x. So when I do this, and also the other part of this is that I don't want it to exactly equal 16. I want it to be over 16, or it could be equal to. Because once I hit that mark, I've hit that benefit portion that helps me pay for school. So here's my translating into an algebraic expression. I got to pick the right inequality, and then here's my 16 hours that I need to make. So they simplify this, and what they do here is a nice strategy to work with. You could say, well, instead of having this complex fraction, maybe the first thing I should do is get rid of the fraction by multiplying both sides by 4. Not a bad strategy. And they get rid of that division of 4, and you end up with 20 plus 12 plus 14 plus x equals 4 times 16, which is 64. Well, I can add like terms and I get 46. Basically what allows me to do that is I could go left to right and end up here in this case. But also I could group the like terms, put a parentheses around there, and add those up to 46, which is the associative property. That overrides order of operations if I need to. And I end up with this inequality of 46 plus x is greater than or equal to 64. This is an equivalent equation to this original one because I followed the rules. I used the multiplication principle to get rid of the division of 4, and then I just simplified or added like terms. This isn't the only way to solve this, but this is a pretty good strategy. So then I finish solving this inequality for x because it's easier to guess and check at what those solutions would be. So I end up with x is greater than or equal to 18 because I added a negative 46 to both sides. The additive inverse of 46, which makes that go to 0. We have a property that says that if I have 0 plus x, that means it's just x. So we end up with this. Now what does that mean? So we could do a partial check, and it's a pretty good idea, especially when we have this equals portion too. But even if I don't, I can say, well, what would happen if it was equal? I would like both sides of these expressions to end up being the same value. So they put 18 in for x. They go back to that original expression, put 18 in for x, and do that, and you get 64 divided by 4, which is 16. Hey, that's equal to this number, that's a good sign. So that check can kind of use this equal sign, which is a nice deal to make sure we do this. Now, the answer again would be I need at least 18. Now, the other part here, I need to answer the question. State the answer. Dina will average at least 16 hours of work per week for September if she works at least 18 hours that fourth week. So it'd be nice to be able to figure that out before the fourth week was over, right? Is to make sure that she gets enough hours in to hit her criteria for her financial aid. Now, they don't go through a lot of different ways, but boy, there's a lot of translation in here. They're going to break it down into little statements here to help hopefully get you used to doing the right thing with the inequality symbols. Be careful, remember what solutions really mean. I mean, that's a key component. What do they do that? In the word problems, we're actually looking for specific answers in the form of a sentence. But the prior section of this, we've got to remember we have all the three different ways to represent infinity of solutions. We have graphing, showing a graph on a number line. We have set builder notation, and we also have that interval notation. So when you go through these exercises, again, I talk about it quite a bit. I say things that aren't written here anymore, talking about commutative and associative properties and those kinds of things. They quit writing this in the red, didn't they? But if you're still struggling with that, one way to do this is don't ever take a step without being able to explain why you can do that. And if you do that, you'll start remembering the commutative property. If I change the order of anything, I need to write commutative property. And if you're lost by that, then go back to chapter 1, and they do write out the reason for each step, why they can do that. None of those reasons have changed. They just start skipping them because they assume you know how to get through that. And that's the end of the chapter. We're going to have quizzes coming up and chapter tests coming up. Again, there are a lot of words, a lot of terminology, a lot of translation. Nothing from chapter 1 is gone. You're going to be expected to be able to practice and understand all the principles and properties and strategies that we pulled out of chapter 1, and they're applied in different ways here in chapter 2.